Good morning, everyone. Let's start. In the previous class, uh, I gave a very brief introduction to the problem of data compression, and we saw that we can broadly classify compression algorithms based on two different uh, factors. So one factor is the fidelity or the quality, how good you want the reconstruction or the decompressed file to be close to the original file. Right? And based on this, we classified compression algorithms into lossless compression algorithms and lossy compression algorithms. All right? And lossless compression algorithms were those where the decompressed file should be exactly equal to the original file, or at least equal to the original file almost always. With some small probability, it's allowed to be different from the original file, but at least with very high probability, the decompressed file must be same as the original file. In lossy compression algorithms, it's okay if the decompressed file is never equal to the original file. What you want is that the decompressed file must be close to the original file with respect to some distortion metric. So for example, you could demand that the mean squared error between the decompressed file and the original file should be less than or equal to some pre-specified parameter delta. All right, so lossless compression algorithm. So typical examples of lossless compression algorithms are text compression, database compression, and so on, wherein you want the output of the decompressed file to be equal to the input. Whereas typical examples of lossy compression are image and video compression. Although you have to be a little careful when you say that, because there are also lossless image and video compression algorithms. Okay, so that was in terms of the quality of representation of the output in terms of the input. Now, depending on the length of the compressed sequence, we can further classify compression algorithms into fixed length and variable length compressors. So fixed length compressors are those for which the size of the compressed file or the length of the compressed sequence, k. So this is only a function of n, the size of the original file, and the distribution of xn, so pxn. So k is a function only of n and pxn. Whereas for variable length compressors, it can be not just a function of n and pxn, but it can also be a function of the realization of the original file. So if you have two files which are drawn from the same distribution, the length of the compressed sequence could potentially be different for variable length compressors. Okay, so now let's see some examples of fixed length and variable length compressors. So for most of this course, we'll focus on lossless compression. We'll explore this in a lot of detail, and maybe towards the end, depending on how much time we have, we'll very briefly cover lossy compressors. All right. So right now we'll see a couple of examples, one for fixed length compression and the other for variable length compression, and it's good to keep these examples in mind. So later on we'll spend a lot of time on lossless variable length compression, and we'll explore that in a lot of detail. We'll see what the fundamental limits are. We'll see how do we construct good compressors, how do we implement them, and so on. Okay. Any questions from the previous class? Any questions? Okay. So let's see an example of fixed length compression. Okay, so let's assume that it's a toy example. So let us assume that the input sequence, the source, is a sequence of length 3. So these are all binary sequences, and associated with each sequence is the probability of occurrence of that particular sequence. Okay, so let us assume that our goal is to compress sequences of length 3. All right, so these are all the possible raw files that can occur. Right, so these are the all possible xns. So these are binary, so it can vary from 000 all the way up to 111. And for this example, let us take the probability of 000 to be half, the probability of 001 to be 1/4, 010 to be 1/8, 011 to be 1/16, and so on. Okay, so these are the probabilities of occurrence of each of these sequences. Okay, so essentially, if this is sequence number 1, this is sequence number 2, and so on. So up to this point, the probability of occurrence of the sequence is basically 1 over 2 to the I, where I means that this is the ith sequence in this particular order. Okay, and the last sequence also has probability 1 over 128, just so that these probabilities sum to 1. Okay, so this is the source. So this is the complete description of the source or the raw file. All right, and so here is the encoding that I'm going to do. This is going to be my compressor. So if the compressor sees the sequence 000, it is going to output 00. If it is 001, it is 01. If it is 010, it is 10. If it is 011, it is 11. And similarly, if it is 100, it is 00, 101 is mapped to 01, and so on. So this is the raw file, and this is the compressed file. Right? So compression is basically either you can store this table, the compressor stores this table, and it just does a lookup. Okay, or another way to implement this compressor is you just remove the first bit of the raw file and keep the rest. All right, so that is what the compressor is going to do. So the encoded version of x1, x2, x3 is basically just x2, x3. Okay, this is one particular compressor. I just came up with this. Okay, now one thing to note here is that multiple source sequences are mapped to the same compressed sequence. Right, so 000 gets mapped to 00, and 100 also gets mapped to 00, and so on. So you have two raw sequences or two source sequences getting mapped to the same compressed sequence. Okay, so this is the compressor, right? So this is only one half of the compression algorithm. Now I need to also construct the other half of the compression algorithm, right? And one thing to note is that this is a fixed length compressor because k. So here n is equal to 3. The length of the source sequence is equal to 3, whereas the length of the compressed sequence is equal to 2. All right. So every compressed file has length 2. Okay. So now I also want to construct a decompressor, right? So the decompressor has to somehow reconstruct one of these sequences given this particular sequence. So can you tell me what would be a good decompressor? Or how would you, suppose that you were allowed to choose a decompressor, what do you think would be good? So if the decompressor sees 00 as the input, what should it output? If it sees 01 as the input, what should it output? Any suggestions? So if
Zeros and
I have one.
yes,
for first one like 00, we expect it to be all zeros only because
okay,
one the
so
highest probable one.
okay, and 01,
001.
okay. So one suggestion is to make sure that so now corresponding to 00, remember that for the compressed sequence 0, 0, if you look at this particular table, the actual source sequence could have been 0, 0, 0 or 1, 0, 0. Similarly, for 0, 1, it could have been 0, 0, 1 or 1, 0, 1. And for 1, 0, it could have been 1, 0, 1, 0 or 1, 1, 0. And the same for 1, 1. Right now, there is no way of distinguishing or no way of finding out whether it was actually 0, 0, 0 which occurred or 1, 0, 0 that was occurred. The first bit is completely lost forever. But one suggestion was that, okay, so we should map 0, 0 to 0, 0, 0 because the probability of this occurring is more than the probability of this occurring. Right? The probability that the true sequence was 0, 0, 0 is half, but the probability of occurrence of 1, 0, 0 is only 1 over 32. Right? So at least if I always select 0, 0, 0, then there's a lower probability that I'm going wrong. Right? 0, 1, 1. So this would be the decompressor. So the decompressor basically does the following. So given whatever y1, y2, it is going to output 0, y1, y2. Okay, so this is a very simple compressor and a very simple decompressor. In general, it could be a much more complicated function. Okay, all right. So now we've seen that. So the rate of this particular compression algorithm is 2 over 3, right? But can someone tell me what the probability of error is going to be? When does an error occur? Yes, Anand, your voice was not audible.
It will be the sum of all the probabilities when the 1 occur. So 1
Okay.
over 16.
1 over 16, you mean 1 over 32 onwards?
Yes, sir.
Yeah. So you know that whenever any of these sequences occur, the output is going to be exactly equal to the input, right? Because if 0, 0, 0 were the actual source sequence, then the compressed sequence would be 0, 0, and the decompressed sequence would again be 0, 0, 0. But then whenever any of these sequences occur, you're going to make an error. Right? So the probability of error is the probability of seeing either 1, 0, 0 or the probability of seeing 1, 0, 1 or probability of seeing 1, 1, 0 or seeing 1, 1, 1. So the overall probability of error is the probability that you see any of these sequences. So the overall probability is the sum of these probabilities, right? So can someone tell me what this is going to be?
One over 16, sir.
It's going to be 1 over 16. Right? So, okay. So this is an example of a fixed length compressor whose rate is 2 by 3 and the probability of error is 1 over 16. Okay, fine. So it's clear that you obtain some level of compression and the probability of error is whatever, it's small. Okay. So now let's look at a different example. So it's the same source. We'll take the same xn and the same pxn, but now instead of constructing a fixed length compressor, I'm going to construct a variable length compressor. So what I want is that the I don't want any error at all. The output, the decompressor should exactly give me the true source. Okay. And therefore, I'm going to choose my compressor in the following way. So this is one possible compressor. Okay, so this is what the encoder or the compressor is going to do. So if the source sequence is 0, 0, 0, it is going to output just bit 0. if the source sequence is 0, 0, 1, it is going to output 1, 0. If it is 0, 1, 0, it is going to output 1, 1, 0, and so on. Okay, so this is, so you can think of it in the form of this particular table. There's an easier implementation for this, and it basically works in the following way. So if this is the first sequence, the second sequence, and the third sequence, and so on, what the encoder is going to do is that it is going to add for the ith sequence, you are going to have I minus 1 once, and then unless it is the last sequence, you are going to add 1, 0. Okay, so this is what the encoder is going to do. All right. Now the decoder, it's fairly simple. Once again, the decoder just reads till it gets just reads the compressed sequence, and since there is a one-to-one map between the source and the compressed sequence, you can always recover the original sequence from the compressed sequence. Right? So going back from here to here is straightforward. All right. So in this case, the probability of error is equal to 0, right? Because there is no error at all. Okay. Now, what is the expected length going to be? So it is the summation over all possible sequences, the probability of occurrence of that particular sequence, times the length of the sequence, length of the compressed sequence. Right? So it is going to be half into 1 plus 1/4 into 2 plus 1/8 into 3, and so on. Can someone maybe compute this and tell me what it's going to be?
1.98.
1.98, is it?
Yes, sir.
So it is 1.98. All right. So now this was 1.98. But then with this fixed length compressor, we got 2 bits, right? So the length is always equal to 2. Whereas in this case, we achieved an even smaller compressed length, but this is achieved only on average. The expected compressed length is 1.98 bits. Whereas in this case, the compressed length is always fixed, but it is equal to 2 bits. You can't get it down below 2 bits if you want a probability of error of 1/16. Right? So this is nice. So we achieved a variable. So we designed a variable length compressor for which the expected length is only 1.98 bits, even lower than the previous case, and the probability of error is 0. Right? We're never making an error. But what is it that we're trading off? So we're trading off the maximum length, right? So in the previous case, the length was always equal to 2. The compressed length was always equal to 2 bits. Whereas in this case, the maximum size of the compressed file or the compressed sequence is, in the worst case, it is 7 bits. Right? So Kmax is 7 bits in the worst case, but in the best case, it is 0. So in this case, we are achieving compression, but only for certain sequences, right? For many others, for all of these sequences, the compressed length is larger than the actual length of the actual sequence. But that's okay, because these sequences are not going to occur very often. So on average, you're going to get very good performance. So on average, you're going to get 1.98 bits. All right. So this is an example of a variable length compressor, and this was an example of a fixed length compressor. Both are lossless compression algorithms. Of course, this is almost lossless because there is a certain probability of error, whereas in this case, the probability of error is exactly equal to 0. Okay, any questions? Any questions? Okay. Fine. So now that we know how to distinguish between lossless compression algorithms, let us see how do we evaluate the performance of a compression scheme. So suppose that we are given two compression algorithms, how do we say that one is better than the other, right? So once again, since we have different classes of compressors, we need different metrics for each of these, and these are metrics that we just saw. So for a fixed length compressor, obviously, if you want to achieve a, a rate which is less than 1 or a non-trivial rate, then some of the sequences are going to be in error. You're not going to be able to recover the input exactly if you demand that k is fixed, right? Because obviously two different source sequences will have to be mapped to one compressed sequence. So there is an associated probability of error. So one way of evaluating the performance of a compression scheme is, of course, using the rate, the size of the compressed file divided by the actual the size of the source file. Right. So k over n is called the rate, and we want the rate to be as small as possible. At the same time, the probability of error, that is the probability that xn hat, the decompressed file, is not equal to the true source file, we want this also to be small. So the goal, if you want to design a good fixed length compression algorithm, we want to make sure that the rate is small and the probability of error is also small. Okay. And typically we will be interested in the regime where the source file is very, very large. All right. So in the regime where n is very, very large. So typically when one analyzes fixed length compression algorithms, we typically demand that the rate must be as small as possible, for a given probability of error, or we can say that for as n tends to infinity, we want the asymptotic rate to be as small as possible and the probability of error to be vanishingly small. So the limit as n tends to infinity of the rate should be as small as possible, and the limit as n tends to infinity of the probability of error should be equal to 0. Now note that this particular statement over here does not mean that the probability of error is exactly equal to 0. All this says is that it becomes smaller and smaller, vanishingly small, but it may never be equal to 0. So it's possible that you could achieve a probability of error which is decaying as 1 over n. Right? So the limit as n tends to infinity of the probability of error now tends to 0. But for every finite n, the probability of error is strictly greater than 0. It's tiny, but it is strictly greater than 0. All right. So this is how one would evaluate the performance of a fixed length compressor. On the other hand, if we have a variable length compressor, we know that you never make an error, right? We demand that the probability of error is exactly equal to 0. Okay, so we typically look at 0 error variable length compressors. This is what we ask for. And the performance is measured using the expected length. So since k is now a function of xn, so for different source sequences, k could be different. The length of the compressed sequence could be different. So you want to make sure that on average, the compressed file is small, right? So we want the average rate to be as small as possible. As possible. Okay, any questions here? Okay. So now the question is, suppose, so now I have a bunch of constraints. I want a fixed length compressor for which the probability of error is vanishing in n, and I want this rate to be as small as possible. So if I give a particular source, then what is the smallest rate that I can achieve for a fixed length compressor? And similarly, for a variable length compressor, I want 0 error. So what is the smallest rate that I can possibly achieve? So these are questions we want to address in this particular course. And we also want to know how do we design compression and decompression algorithms such that the actual rate is close to this optimal rate. Okay. And remember, we are always interested in the regime. Okay, not always, but typically we are interested in the regime where the file size is very, very large. Because after all, if the file size is small, then there's no need to compress at all, right? We're really interested when n is large. So it turns out that we know the exact answer to how small the compressed file size can be for a large class of sources. Okay, and this is a very old result going back to 1948 by Claude Shannon. Okay, and it says the following. Of course, it's a simplified version of what Shannon originally proved. This can be proved in general for a much larger class of sources. But let us now assume that the source file is an IID sequence. Okay, the source sequence is in, so each symbol in the source is independent and identically distributed. This is not a very realistic assumption because actual files don't have sequences which are independent and identically distributed. But nevertheless, let us make this very simple assumption. So it says the following: if the sequence is IID, this is also sometimes called a memoryless source. So for memoryless sources, it is possible to construct compression and decompression algorithms or encoders and decoders for which, of course, the probability of error should tend to 0 as n tends to infinity, but the rate as n tends to infinity is close to the entropy of the source. Log 1 over px of x. So it is possible to construct compressors for which the asymptotic rate is equal to the entropy or arbitrarily close to entropy. To be more precise, this is equal to entropy plus some epsilon. Okay. So you can get arbitrarily close to entropy, and you can also achieve a vanishingly small probability of error. So this is actually one part of the so-called lossless source coding theorem. This is again, remember, for fixed length compression. But there's also a second part to the lossless source coding theorem. It says that now of course, it's possible to construct compression algorithms for which the asymptotic rate is close to the entropy. But then then the natural question which comes up is it at all possible to compress at a rate below the entropy? And what Shannon showed was that no, it is not possible. If you ever try to construct a compression algorithm, no matter how much computational complexity you put in, no matter how many resources you put in, if the sequence is IID, and if you try to compress this at a rate below the entropy, so no matter how you choose your compression and decompression algorithm, if the asymptotic rate is strictly below the entropy, then the asymptotic probability of error is never equal to 0. The asymptotic probability of error, in fact, tends to 1 as n tends to infinity. All right. So the lossless source coding theorem says that if you want to compress an IID sequence, you can achieve an asymptotic rate which is close to the entropy, but never below the entropy. Okay, so the entropy is in some sense a fundamental limit for the lossless source coding problem, or the fixed length lossless source coding problem. So if you look at the optimal compressor, so if you vary the rate for a given px, so you fix a particular source, you fix a particular px, and for each rate r, you try to construct the best possible compressor, that is that compressor which achieves the least probability of error for a given rate. Okay, the minimum probability of error. The source coding theorem says is that what the source coding theorem says is that if you're operating at a rate above the entropy of the source, then the probability of error is really tiny. So it's very close to 0 for large n. But then if you try to compress at a rate even slightly below the entropy, then the probability of error is very close to 1. All right, but remember, this is not for a fixed compressor. For each R, you will choose a different compressor, the best possible compressor for that particular rate. All right. Any questions here? All right. So this, of course, holds for memoryless sources. In fact, this particular, yes.
Sir, here you said it can't be below the entropy. The asymptotic rate can't be below the entropy, no, sir. So that h of x plus that epsilon means like. Can you take an example, sir? Like,
well, it simply means that. Sorry, yeah, please complete.
So entropy it's like above that if we take even a small value epsilon or something. So like when you're trying to compress, we want to have minimum number of bits, no, sir. So
Correct,
why will we go above entropy? So we will fix to entropy value only when it is IID.
That is true. But then a subtle point here is that the probability of error will depend on how far you're above entropy. Okay, so if you choose a slightly larger epsilon, maybe epsilon equal to 0.1, then the probability of error is going to, of course, the probability of error is vanishing in n, but for a given n, the probability of error is smaller if you choose a larger epsilon.
Okay.
All right. So there's of course this trade-off. So if you choose a slightly larger rate, then you can achieve a smaller probability of error. But then if you're only interested in the first order asymptotics, then it doesn't really depend on the probability of error, right? No matter, or it doesn't really depend on epsilon. So as long as epsilon is positive, the probability of error is asymptotically going to 0. But the actual probability of error for a given n will depend on epsilon. All right. So that's a good question. But then what this says is that if this epsilon, if I take r equal to h of x plus epsilon, if epsilon is negative, then the probability of error will tend to 1 as n tends to infinity. So the higher you are from, so that if the rate is higher than entropy, then the probability of error will of course depend on how far you are from entropy, and similarly the negative way as well. The smaller the rate you try to target, the larger the probability of error for a given n. But asymptotically, as n tends to infinity, this will tend to 1, whereas in this regime it will tend to 0. So for a fixed n, it is not exactly going to look like this for finite n, but as you let n tend to infinity, it's going to get closer and closer to this sort of step curve. All right. So in fact, this statement can be generalized. It is not just for IID sources, but as long as if xn is distributed according to pxn, which is stationary and ergodic, then it is possible to achieve the minimum rate of compression that you can achieve turns out to be equal to this quantity, the limit as n tends to infinity, h of xn divided by n. This quantity is called the entropy rate of the source. This is called the entropy rate of the source, and basically the same an analogous result holds. So it is possible to design compression algorithms for which the probability of error tends to 0 and the rate is arbitrarily close to this particular quantity, the entropy rate. But then if you try to compress at a rate below the entropy rate, then the asymptotic probability of error tends to 1 as n tends to infinity. All right. But the proof of this is much more complicated. This at least the result is simpler, but remember all we are saying here is that there exist encoders and decoders which achieve this particular rate. I'm not saying what the computation how easy or difficult it is to construct these compression algorithms. In fact, the way Claude Shannon proved it, it is not a practical algorithm. All right. So the complexity, the computational complexity of compression and decompression grows exponentially in n. So it's not a practical compressor. All right. But then it is possible to construct more efficient compression algorithms. Okay. So the result, a similar result even holds. Yeah. Any questions?
Sir, what does ergodicity mean?
Okay. So ergodicity at a high level means that time averages converge to the ensemble averages. So basically, if you take a sequence, okay. So for example, if you have an IID sequence, right? IID according to some px, and you look at the empirical frequency of letters in xn, right? So let's say mu a of xn is the frequency of occurrence of the symbol a in xn. all right? If this is an IID sequence, as n tends to infinity, what do you expect this to tend to? So for large n, what do you expect the number of A's to be? So if you're saying, let's say that you're tossing a coin maybe n times, and you count the number of heads. For large n, what do you expect the number of heads to be?
Px.
Px, right? So in this case, you expect this to be close to Px of A if n is sufficiently large. So this is IID, right? Now, in general, if this is an arbitrary stationary sequence, then it may or may not be the case that the number of occurrences of a particular symbol is equal to Px of A. All right. So for example, let us take the following sequence xn, which is described as follows. So x1 is distributed according to Px from distribution. Maybe let's take a Bernoulli sequence, maybe Bernoulli half. All right. But then if I want to construct a dependent sequence. So let us assume that x2 equal to x3, all of them are the same and equal to x1. Okay, so this is a sequence which has memory, right? Because all the symbols are going to be the same and they're going to be equal to x1. All right, so for any I, what is Pxi of A going to be equal to?
Half.
Sure, half or whatever. It's going to be Px1 of A, right? Or in this particular example, if you assume that this is Bernoulli half, it is going to be equal to half, right? But then if you count the number of ones or the number of zeros, right? What would this be equal to? What would be the frequency?
This probability into n.
I'm not talking about probability. So let's take any particular sequence. What will happen? What can happen? Exactly, as Anand points out, it's going to be all zeros or all ones, right? With probability half, you're going to see the all zero sequence. With probability 1, you're going to see the all one sequence, right? So mu A of x1 is either going to be 0 or 1. All right, with probability half, it's going to be 0. With probability 1, it is going to be 0. So, but then the probability of occurrence of x1 or any xi is half. So in this case, mu A of x1 is never going to be equal to a half, right? For any particular realization. So the probability that mu A of xn is very close to the true probability is very, very small. All right, with very high probability, it's never going to be close to the true probability, right? So this is a sequence which is not ergodic. Because the sample mean or sometimes called the time average, is never going to be close to the ensemble average, which is the true probability. All right. So these are sequences which are not nice, and we want certain nice properties in the true source sequence if we want to be able to compress them efficiently. All right. So it turns out that a stationary sequence is of course one where the probability of any set of random variables is invariant to a time shift. Right? And ergodicity basically says that time averages should be close to the ensemble averages.
Sir?
Yes.
Sir, this I didn't understand, like how you said all zeros and all ones.
Okay.
Like
So yeah, go ahead. Go ahead.
yeah, like to take mu a of xn equal to 0 or 1, you said either all zeros or all ones. We're
Correct.
just saying that the probability that any that x1 taking value a is half. So uh, just asking, can't we get a sequence 1 0 1 0 1 0 or
No,
what?
right? So I'm saying that with probability 1, x2 is going to be equal to x3 is going to be equal to x4, and all of them are going to be equal to x1. So it's a dependent sequence of random variables.
Why we are taking, or it's just
So
an example?
this is an example that I am considering.
Oh, okay.
Right? It is a sequence with memory. It's not a memoryless sequence. It is not an IID sequence. So obviously there's a lot of dependence among the random variables, and it's a simplistic assumption, whatever. It's a toy example, but this is an example where all the random variables are equal with probability 1, and they're equal to the first random variable x1, and x1 is distributed according to px.
Yes. Okay.
Right?
So this is just a example to
It's just an
put a
example. Yes.
non-ergodic case.
Exactly, exactly.
Thank you.
So we were interpreting rate as the entropy, sir. But here, like in the above statement, if you scroll up, you've written as entropy by rate, like h of x divided by n, sir. This R
Okay,
minimum,
so
sir.
uh
So how do we interpret in this particular thing, sir?
okay, so the true minimum rate of compression is this quantity. It is the limit as n tends to infinity of h of xn divided by n. So let's look at this. So R min is equal to limit as n tends to infinity h of xn, which is basically h of x1, x2 up to xn divided by n. This is the entropy rate for any stationary and ergodic sequence of random variables. And in particular, an IID sequence is also stationary and ergodic, so it should hold for IID as well. All right. So what can you say about h of x1 through xn for an IID sequence?
N into h of x1.
Exactly. So h of x1 through xn, just using the chain rule. So this is summation I equal to 1 to n h of xi given x1 up to xi minus 1. But what is this equal to? So since these are IID, it is simply each of these is equal to h of xi, which is equal to h of x1, which is h of x. So this quantity is simply n times h of x. All right, so this is n times h of x divided by n. The n and n cancels, and this is just equal to h of x or h of x1, whatever. This is specifically for IID. Is that clear?
Yes, sir. Thank you.
All right. Any other questions? Right. So for most part, we'll assume that the sources that we have are pretty simple. They're either memoryless or they have a small amount of memory. We may assume that there may be first order Markov chains, but we won't really go beyond that. The main point of introducing this concept of stationarity and ergodicity is just to let you know that these are very general statements which hold for a very large class of sources. But of course there are restrictions. We know what the optimal rate of compression is under this particular assumption, stationarity and ergodicity. Now there are certain applications where the source is not stationary, it's not ergodic, it's not in the form of a sequence sometimes, right? So if you want to compress, say, graphical data and different kinds of data, the theory that we will develop and the kind of algorithms that we will develop will not be applicable. They won't be good in many of those cases, for which, I mean, a lot of those problems are still unsolved. But at least for sequential data, which have these nice statistical properties, we know what the best, we know what exactly is the best that we can do. All right. So a very similar statement also holds if you want to do lossy compression. And how does that differ? So suppose that we want to design a compressor for which the average distortion between the input and the output is less than or equal to some quantity. So basically, I'll define a function d. All right. So it takes two inputs, the input symbol and an output symbol, and okay. So for example, just think of this distortion as maybe the mean squared error between the input sequence and the decompressed sequence. Okay, so that's the distortion function. So we need some measure of reliability of the compression algorithm. So for a fixed distortion algorithm, for a fixed distortion function, we want to know what is the minimum rate of compression that we can achieve. Okay, where the target distortion is some n times delta. Let's say that the mean squared error must be less than or equal to n times delta. Then it turns out that if xn is an IID sequence, then once again we can make a similar statement. We can construct encoders and decoders which are less than or equal to, for which the asymptotic rate is less than or equal to this function r of delta, and the expected distortion, the average distortion, is at most delta. And if we try to compress at a rate strictly less than this whatever function r of delta, then the average distortion must be greater than delta. So this r of delta, which is called the rate distortion function, the rate distortion function turns out to be this quantity for a given delta, for a given d, and for a given input distribution px. The minimum rate of lossy compression is basically given by this function. So it is a minimum over all possible the minimum over all possible distributions, all possible px hat given x, such that the expected distortion is less than or equal to delta of the mutual information between x and x hat. So this is some quantity which can be obtained by solving an optimization problem. So if you solve this optimization problem, you're going to get some number, and the minimum rate of compression turns out to be equal to that particular number. So this is a function of delta, the distortion function, and px. All right, and this is called the rate distortion function. So this is just a statement that I'm making at this point, just to give a high-level overview of what kind of results are known in the literature and what is the best that you can do. But here the specific assumption is that we are modeling our fidelity criteria as using this particular quantity. The expected distortion should be less than or equal to n times delta. Okay, under this criteria, the minimum rate of compression is given by this quantity. Remember, note that this quantity does not depend on n, right? It's a single letter expression. It depends only on px, it depends on delta, it depends on what distortion function you choose, whether it is squared error distortion or something else. And you can basically obtain this by solving some convex optimization algorithm. All right. Any questions? Okay, so we'll stop at this point. But before the next class, you should revise some of the basics you've seen in the information sciences or information theory course. So in particular, the definitions of entropy, joint entropy, conditional entropy, mutual information, conditional mutual information, KL divergence, and the relationship between mutual information and entropy, the chain rules of entropy, and the fact that all of these, at least for discrete random variables, all of these quantities are non-negative. Okay, so these properties, we will use these properties in the rest of this course. So you should be completely familiar with these notions. Okay, we won't be using too much beyond this. Anything else we'll sort of derive from scratch, but you should be comfortable with at least these definitions and these relationships. Okay, any questions? Okay, so if not, then we'll meet in the next class. So see you then.